We busting ass the last 3 weeks of the job to get it done and out because they're already 3 months behind because of all these delays that weren't found. I mean, this one right here, that's the main relief air plenum, and the electrician's running conduit right through it. Something like this is going to happen well before that piece of ductwork is installed. Well, then what happens? Well, then we got to re-excavate the outside the building footprint, rerun that conduit, drill new holes. You probably already got equipment in that room that now you have to protect from the water, from the concrete core driller. And see here again, we can just make sure. Previously there were some pipes here that were in the beams instead of between the beams. So yeah, it is something that HB has invested huge sums of time and money into making that change. And that's one of our company philosophies is, educating the workforce and giving back to the community. We want to be the most trusted and most sought out general contractor in the Southwest. Well, how can we do that? We don't do change orders. A lot of these other owners we talk to, they hire other contractors, and the moment they sign that piece of paper, that change order machine starts. Oh, well, we're going to need more money for this. We're going to need more money for that, so on and so forth. We just don't do that. In fact, show you another project. Well, I'd like to show you guys another project. Any questions on this one?
Just touch on the system itself, just to close circle on that. You guys understand the gist? I mean, once you take away the access flooring, the floor plenum space, it's a very simple mechanical system. It's a hydronic-based system. So you have something that creates heat, the boiler. You have one pipe that sends that hot water out, one pipe that brings the water back. You have a cooling tower, which is a phase changer, or your condenser that sends out cold liquid and takes warm liquid back and makes it cold again. That tempers the air. That's a basic 4-pipe hydronic system. You'll see that in, 60% of the buildings in New Mexico. It's a very efficient building, or a very efficient system. Everybody knows how to use it. It's easy to maintain. The life cycle cost is not that bad to swallow over like a 50-year life cycle cost of the building. And you'll be dealing with a lot of systems that are similar to that.
Could you show us where that hydronic system is located? And how do you direct the hot air direct the air from the ducts then to the coils?
So we were just in the basement and I've changed that model already. But what I can say is, so with the access flooring panels turned back on, you see these long red diffusers. And just like those lineal diffusers up there, that's where the air is coming through. The difference is that typically there's going to be a box that has a coil somewhere outside this room that's feeding ductwork after the coil to get the air to each one of these diffusers. In this setup, the air under the floor is all one consistent temperature, typically 55, 60 degrees. And then as the air goes through this terminal unit, you have your coil within that unit that then heats or cools the air.
So the majority of UNMs on the 4-pipe fan coil system like this, the central plants that you see all over the place, because when you do a large campus like this, you can afford to build a very large boiler or multiple sets of very large boilers or very large phase changers, condensers, cooling towers. And then you can then run these pipes all over the place. And as you build on over the life of your campus, it's really easy to tap into those. There's a large cost up front to get that infrastructure in place, but then down the road, as you add buildings or change buildings, you have less of a cost of the project, because you're already set with the infrastructure. It's like a lot of the sidewalks here on campus, they're not really sidewalks, they're actually tunnels. You know, you'd be walking along, especially like over by like Castaner Hall and Ferris Engineering, all those sidewalks are actually tunnels, and inside those tunnels are all the, you know, the boiling pipes, all the cooling pipes, and that sort of stuff.
But for a project like the library, a standalone building, it's not cost effective. Okay, so this is now Sandia High School Math and One Computer. Math and Science building. Okay, this is a much more complicated system. APS, Albuquerque Public Schools, has been pushing for years for a 4-part system. It's got an economizer, it's got a swamp cooler, it has air conditioner, actual refrigerated, heating and cooling system. It's 4 separate components which make up that system, and each one has to know when to turn off, each one has to know when to turn on. It's based on heat load, cycling, climate, time of year. It's all programmed to work so that the energy costs are as low as possible. And the economizer, it runs during the late hours of the day, say generally spring and fall when it's 70 degrees outside. There's no need to run a refrigerant and all that, the compressors and the pumps to pump the refrigerant through the system, when you can basically take the outside air and put it straight in the building after running through filters, obviously, because the exterior temperature is appropriate. Then you have the swamp cooler, which is like most people have on their houses out here. During the hot summer days, we're very dry here, so it makes a lot more sense to cool the building down by water instead, again, of refrigerant and pumps, compressors. Then during the extreme heat of the summer and extreme cold of the winter, you have the actual refrigerant heating and refrigerant cooling system. So it's a, uh-oh. All right, can I get this back on? There we go. So it's a much more complicated system than what we just seen at the library. Yes, sir.
I imagine you have products that you use already model existing in your system, maybe in new place, but when it comes to really complicated systems, do you often have to remodel or model just for specific parts of the system if it's really complicated, like to make your own components or families or whatever?
We do, but for the most part, a lot of the manufacturers they'll do that for you. I mean, mechanical, electrical, plumbing part of your project is going to cost roughly 35% of the total cost. So, $10 million project, you know, $3.5 million of that is going to be mechanical systems. The $3.5 million, the guy that's providing you the air handlers, the boilers, the pumps, the valves, they've got somebody on staff that will do that for you. Sometimes we do have to make custom families. I think you have to do that every now and then, but for some of the larger components, we can generally get that from the manufacturer themselves. We usually have somebody on board that's dealing with that sort of stuff. Because like large air handlers like this, they're not off the shelf. All of them are custom. That's why it also takes a long time to order this stuff and to get it out to the site. Is it doesn't exist right now. If you're in a building and you want a large air handler, like yes, you could call it the Train or all the other manufacturers say, I want this various model. It's not built. It's all custom. Every bit of it is custom. I mean, there's certain components with it, like the circuitry, condensing units, the fan coils, that sort of stuff is off the shelf, but the overall component itself is all custom. They'll have somebody that helps you to put that together.
Every project they're custom?
Every project. This project, talking to the workflow, every now and then we do get to work, well, half the time I'd say, we do get to work with a firm that is working in Revit. Shocking, we still work with a lot of firms that still use AutoCAD. This project was done like in some third-party freeware, it wasn't even AutoCAD, I don't remember what it was. And Chris had to model everything from scratch.
Now, in the scenario, we have two scenarios, I think, that might address what you're saying. If we're going into an existing building where we're gutting it out, parts and pieces or whatever, we're gonna demo as much as we can up front, and then we're gonna bring in laser scanners. Because by the time I can actually sit there and pull a tape measure, me and 2 or 3 other guys, it would take us a month just to pull all the dimensions, and then we'd go try to model it, and it would be all wrong and whatever, because human error. Now, with the technology using Autodesk Recap, we can send in, we have a few people in town that do the scanning for us, we send them in, and we get a brand new 100% accurate Revit model as a sandbox that we can now play in and begin moving and adding new systems into. So there's a couple different avenues to take depending on the job. Now, if we're going to gut it out completely to structure, we'll still scan it. Because now we can get the structure and make sure that, yeah, when it says 24-inch beam, it is actually a 24-inch beam.
This is the future, so it's kind of like with LEED. When LEED first started out, it's hard to find LEED acceptable low VOC type paint or sealants or adhesives per se. And then once it caught on and became normalized, then everybody offered it. There was no premium for the cost. It was easy to get. With specific components in the building, since this is the future, it's becoming more normal now. So more and more manufacturers are on board with helping you and providing you with what you need to put your model together to make sure that their system works. They're not slammed at the end of the day.
So again, just the complexity of this, you know, prior to 3D ability, I came from it. You know, I was the guy who was sitting here with those 3 badasses I was describing earlier, trying to figure out how to make all this stuff fit. And sometimes we'd end up with the situation where we had to go back to the engineer, had to go back to the architect. We couldn't make that decision in the field. And then we're sending guys home for 3 or 4 days without pay because we can't continue work. Well, again, this process, James mentioned the CA process being reduced. We can make a phone call now and say, hey, we've got a situation, here's our suggestions. All right, well, good job, thanks for finding that, let's do this. Finalize it with the formal RFI. Well, bam, we can get all these questions answered as we're still coming out of the ground, even before steel goes into fabrication, and it reduces those amount of delays. Specifically, I wanted to show you on this project because it's a much more complicated system, but this is a personal, like, hey, good attaboy for HB and for me. If you notice, when we finally modeled all these complex components that were supposed to fit in the room, the mechanical room was supposed to turn back into the building at this yellow column. The mechanical room was supposed to stop here. And this was an outdoor patio. So imagine your mechanical engineer, he says, oh yeah, we're going to draw all this stuff and it's going to fit in that room. And we finally do, and this entire unit's outside. Okay, so again, before fabrication, hey, Mr. Architect, Mr. Engineer, we got a situation, let's look at this together. We come to the table with 3 suggestions. APS tells us, nope, we've had these gross hybrids of this because of money, because of time, because of delays. You guys are finding it now. We don't care what it costs. Let's make it happen. Boom, we had a week. Go back to the drawing board, figure out how to move stuff, figure out what we could do. All we did was added a couple more pieces of steel to elevate the subfloor to get the concrete to the same elevation, and threw in 1 more column. Bam, problem solved. We lucked out in the sense that this was an exterior outdoor patio deck, and the pavers for that deck were so much more expensive in relation to the little bit of extra steel and concrete we needed that thankfully, since we caught it before anything was built, we were able to give APS a credit back for $100,000 instead of 6-month delay to the project. Who knows what kind of hybrid, half-assed mechanical system, and who knows what kind of additional struggles we would have had. But again, use the technology we have, guys, and move on. Let's figure out how to make our industry better. We're the only industry who is still back in the 1940s in relation to any other automobile factories, airplane factories, so on and so forth. Yes, sir.
Do you guys have standards, like trim standards for, like, basically, like already set up and outlines that your subs have to follow? Or?
Absolutely. It's the only way it works. You know, you can't play baseball if you don't know the rules of baseball. And you can't play football if you don't know the rules of football. Well, you can't play BIM if you don't know the rules of BIM. And one of the very first things we do is once we get all of our parties together, once we get all of our parties together, we know who's the pitcher and who's the batter and who's the first baseman. Now we go over, okay, well, you're responsible for this, you're responsible for this, you're responsible for this by this time or else. And that's the only way it works. Yes, sir.
Why would you say that the construction field area is so behind automobile or other engineering?
Because we built the Empire State Building in 7 months. How big was that? And now it takes us 9 months to build a 5-room dental office? The Empire State Building had to be planned by the minute. For instance, the local restaurant here in town, we'd close it down on Sunday night at 8 o'clock. We would reopen Thursday at noon. We would completely gut it out to framing and floor, and everything would be brand new by Thursday at noon, working all nonstop from Sunday night. That took hour by hour planning. We don't do that anymore. We just don't do that anymore. Now we can sit and we got 2 weeks for the architect to answer the RFI, and then we have 2 weeks to evaluate it and see if we need to do anything differently with it. It's the technology we have, it gets rid of all that. And that's why it's allowing us to help our industry get improved.
It's also because, so like a technology factory, you're producing one product over and over and over again. There's efficiency and repetition. Every building is unique, unless you're doing some sort of prototype building. And there are industries or certain owners that require prototypes, reproduction, the same thing over and over. But for the most part, I mean, if everybody in this room is going to be designing the same building over and over and over for your entire career, I doubt anybody in this room would want to be an architect, right? There's that side of the equation. The other side of the equation is actually a cultural thing. The people that go into construction are generally not that well educated. I mean, this is all field education. This is on-the-job training. You don't get a degree and go say, I'm going to be a laborer on a job site. You know, project managers, some of the sort of higher echelons of construction, they're trying to make sure that we're creating a more efficient process, more efficient way for creating a built environment for human beings. Yeah, you have higher education there, but for the most part, I mean, you have a tradition of, a cultural tradition of folks that didn't want an education, so they went and got it out on the site. They got a trade, you know, and so trades historically just have not been very technologically savvy. I mean, it's just the cold, simple fact of it. And the other cold, simple fact of it is construction still is very inefficient. It's still very cold and uncalculated. I mean, Chris was talking about Empire State Building back then. So my general background, my general responsibility is estimating. I figure how much everything costs. Back then, when we did a building in the turn of the century, during the Industrial Revolution, for every $1 million of construction, you estimated a fatality. You know, that's how inefficient it has been and kind of still continues to be. So we're starting to switch over. You know, with technology like this, you are standardizing and you are being able to reproduce and get the efficiency out of reproduction that you would in a factory, per se. But for the most part, you still have lots of the industry that just has not embraced technology. You know, we're just, like I said, the construction and some of the design professional industry is still rife with Luddites who just refuse to embrace the future.
So, you know, like, there's a lot of pride, especially when you've been busting your ass outside in the cold and the hot for the last 20 years. Somebody, some young whippersnapper comes in and tells you, oh, you're gonna have to do it this way now. And you gotta learn how to use a computer. Well, that can sometimes not be taken the best way by some. But then you get the foreman, and you get one or two guys that are actually excited to do it. And they start figuring things out for themselves. And now Mr. Superintendent, who's been doing it for all these years, he's not needed, because the foremen are figuring it out. Even the laborer who can now operate the computer, he can figure it out. He doesn't need the superintendent. So just like any new technology, all of a sudden, the superintendent has no choice. If he wants to keep himself viable, he's got to. Or the 20, 30-year foreman as well. So this is another very complicated mechanical system. I'm going to get this other model loaded. This is Rio Grande High School freshman building. This is a Daikin system. So typically, the two previous systems we saw, we're talking big 4-inch pipe, supply, return, cold, supply, return, hot, from cooling towers of boilers reducing down to 1/2 inch or 3/4 inch piping. Well, this Daikin system there's only 3 systems now in the state of New Mexico. The Rio Grande High School freshman building is one of them that hasn't. This piping that you're seeing here, it's 4 inches diameter, because it's actually 4.5 inch diameter, because it's got 4 inches of insulation on it. The pipe itself is only 1/2 inch. It's, anybody know what a mini split system is? You see them on the wall. Typically it's a long rectangular device, and it blows up and down cold or hot air.
You'll see them anywhere you have a server.
If you ever get the chance to walk into a server room, you'll see them in there all the time. Ultimately, you have an exterior condenser, which either gets rid of the heat or brings heat in. And through very small piping, it transfers that refrigerant into the interior module, which is just another fan coil, another radiator, but it has its own air fan in it as well. So it doesn't need a big air supply from somewhere else. Well, this is a very similar system. We've got these individual terminal units. Let me come back down. Well, actually, from here, this ductwork, you got 4 sets. The other model isn't open. The other half of the building isn't open. But you have supply and return. Anybody know what an ERV is? It's an energy recovery ventilator. All right, so we spent all this money in the winter to suck in 40-degree exterior air into the building and run it through heaters so that we could get it up to 55, 60-degree air. Now we send that air through the building, and as it goes through the terminal unit, it's now heated to 70, 75, depending on the occupant's desire. Well, we have to change the air out, otherwise all of us would be asleep right now, right? Typical building like Rio Grande 3-story building has 4 air changes per minute. So that means that, or no, I'm sorry, is it per minute or is it per hour?
Per hour.
Per hour, my bad. All the air in the building is completely exhausted and replenished 4 times an hour. So heating 40-degree air 4 times an hour is a huge expense. You put an energy recovery ventilator on the roof, and what happens is, as that 40-degree air comes into the building, it passes through these really amazingly cool filters. It's like this continuous paper that spins, and by it spinning, it allows the hot air that's being exhausted out of the building to pass by, never touch. They don't ever mingle, but to pass by through this very thin filter, this 40-degree exterior air. And so what it does is, by its spinning and transferring the air past each other, that energy is actually used to heat up that exterior air to now 55 degrees. So instead of having to cool 40-degree air, you only have to, or heat 40-degree air, you only have to heat 55-degree air. That's a huge, huge energy savings and cost savings. The carbon footprint is drastically affected and minimized by these awesome units. So by doing this, you no longer need to have the giant air handler on the roof that's actually heating air to a certain temperature. Because what happens is as those terminal units heat up the air in the building, the ERVs suck in the new air, expel the old air, transfer that energy, and the VAVs can now adjust locally the air temperature as necessary for the occupant.
It's basic thermodynamics. That's why UNM forces you guys to take Physics 101 and 102.
There you go.
Is your EVR, is that the same thing as a heat exchanger?
It essentially, yes, essentially. Just, sorry?
How far apart is the intake and the exhaust?
Within the unit,
Yeah.
they're right next to each other.
There's no possibility of the exhaust being taken in back into the intake?
No, that's a good point. Just like there's codes that say you have to have a bathroom vent no closer than 12 feet to any air supply, the ERVs are designed and built so that the exhausted air is blown up and the fresh air is actually drawn from the opposite side and at a like 30-degree downward angle. So that air is obviously blown in that direction and the fresh air is sucked from the other. So that's taken into account.
What do you guys want to know about the structures now?
Hey, okay, well, that's structures. Let's do this. Let me get rid of all the. Get down to just the structure. So, can anybody tell me what this is? Cross bracing to an extreme. That is brace frame assembly. Essentially, you can see there's two back-to-back. Yeah, there's a pointer over here, doesn't it?
Yes.
This thing? Awesome. Okay, so you got back-to-back brace frame. 3 grid lines later, another. And then you'll notice this is another one going in the opposite 180 or 90-degree direction. You've got another one back here. On a 3-story building, you put those on top of each other, across the length of this building this way, and then you put opposite direction across the length this way, 3 or 4 rows, whatever. I'm not an engineer. And now you have all your rigid and shear bracing that you need outside of any exterior wall application, which allows many more opportunities for your actual exterior finishes, whether it's cladding, stucco, so on and so forth. The design of the exterior skeleton does not have to take into account any of the structural integrity of the building.
Most multi-story buildings now are designed with this sort of structural steel skeleton where your exterior building envelope is not a part of the structure whatsoever. We call it bypass framing because you'll build a skeleton. If you imagine a rectangle multiple stories high, you end up with a tab that comes off the steel and the studs just attach to that. And the studs are mostly at that point just a substrate to put your exterior envelope on. The skin doesn't need to be structural. And for the most part, the efficient way to build large buildings is not having your skin being structural. Plus, skins fail just like they do with any other animal. I always tell people that a building